definition. So homomorphism definition. So pi of a plus b is equals to pi of a plus pi of b. So this is homomorphism first condition, and second condition also is there. So pi of a into b in place of addition. So we are taking multiplication. So pi of a into b is equals to pi of a into pi of b. Is clear? So two conditions. So pi is homomorphism is nothing but, so first condition. So pi of a plus b is equals to pi of a plus pi of b, and pi of a into b is equals to pi of a into pi of b. So previous class definition. So here, so pi of a plus b is equals to pi of a plus pi of b, and pi of a into b is equals to pi of a into pi of b. So these are the two conditions for homomorphism. So is given pi is homomorphism. So pi is homomorphism from R into R dash. So with kernel U. So kernel definition. So kernel U is nothing but, so kernel is nothing but every element in domain, every element in domain. So like this. So this is R. So this is R dash. So this is pi, A, B. So 0, like 1. So kernel definition is nothing but every element in domain. So domain is nothing but pi function R to R dash. So our mapping pi function R to R dash, every element in domain. Domain is nothing but R. R dash is codomain. So every element in domain can be mapped to identity element or zero element in codomain. So here kernel U is nothing but A is mapping to zero element in R dash. So A belongs to kernel U. So which elements in domain, can be mapped to zero element in codomain. So which elements in domain can be mapped to zero elements in codomain. So these are called kernel. So here kernel is nothing but A is belongs to kernel U. Okay? So then, so pi of R is isomorphic to R by U. Here isomorphism. So we have to show that pi of R is isomorphic to R by U. Is nothing but isomorphism is nothing but, we have to show that. So 1 condition, on 2 condition, homomorphism condition. Is clear? So isomorphism is nothing but, we have to show that 1 condition, on 2 condition, and homomorphism condition. So then we can say that, so pi of R is isomorphic to R by U. So these are the definitions. So before going to theorem, so theorem proof. So once again here definition, epimorphism. So epimorphism is nothing but homomorphism and onto condition. It satisfies, so pi satisfies onto condition and homomorphism. You know? So pi is onto and homomorphism. So then we can say that pi is epimorphism. You know? Here also isomorphism. So theorem statement. So pi is a function from R to R dash. Pi is a function from R to R dash with kernel U. Then we have to show that pi of R is isomorphic to R by U. So let A belongs to R. So A belongs to R. Then U plus A belongs to R by U. A belongs to R. Then U plus A belongs to R by U. And pi of A belongs to pi of R. So here, so this is R by U. R by U is nothing but factor group. Factor group. So every element in factor group R by U. So every element in factor group is of the form cosets. Okay? So here A plus U, R, B plus U, C plus U, like this. Every element in factor group or quotient group R by U. U is nothing but ideal. R by U. R is ring. First element belongs to A is belongs to R. U is nothing but same element. So first element is A, and so we are taking another element like B. So B plus U belongs to R by U, where B belongs to R and u belongs to u. It's clear? So this is every element in R by U is of the form u plus A or A plus U, u plus B or B plus U. So we have defined a mapping. So define a mapping. So psi. So define a mapping. Psi is defined by, so psi is defined by, so we are taking a mapping. Psi is defined by, so ఇది ఎక్కడి నుంచి తీసుకోవాలంటే pi of R2 R by U. Question లో is mentioning statement. So pi of R2 R by U. So pi is a function, psi is a function from pi of R2 R by U. So we are taking function. So we define a function. So domain is nothing but pi of R. He is mentioning question. So pi of R and codomain is nothing but R by U. So psi is a function from pi of R to R by U. So then we have to show that psi is isomorphism. Psi is isomorphism is nothing but it satisfies 1-1 condition, on-to condition and homomorphism condition. Okay? So psi is a function from pi of R to R by U. So psi of R to pi of R to R by U. So in R by U is a domain and pi of R is codomain. So given by psi of domain element. So each and every element in domain is of the form U plus A here. And codomain element pi of A. So psi of U plus A is equals to pi of A for all A belongs to R. So this is a mapping is defined by psi of U plus A is equals to pi of A for all A belongs to R. So this mapping is, we have to show that this mapping is isomorphism. So first condition 1-1 on-to condition and homomorphism condition. Okay. So isomorphism is nothing but 1-1 condition, on-to condition, homomorphism condition. So but before going to, we have to prove that isomorphism before the function. We are defining this function psi is well defined function or not. First we have to verify the psi is a function is well defined function or not. Okay. So how to verify the function is well defined function or not? So well defined function is nothing but we are taking x is equals to y. We have to show that f of x is equals to f of y. Okay. So psi is well defined is nothing but, so x is equals to y. We have to show that psi of x is equals to psi of y. For a comma b, for any a comma b belongs to R, u plus a equals to u plus b, like x is equals to y or a is equals to b. So now we have to show that psi of u plus a is equals to psi of u plus b. So this is well defined function. Then we can say that psi is well defined function. U plus a is equals to u plus b. That implies a minus b belongs to u. That is equals to kernel pi. So u is defined as kernel pi with kernel here with kernel u. So u of a plus u plus b is equals to a minus b belongs to u. So but u is equals to kernel pi. So kernel pi is nothing but image of that element should be equals to 0. So psi of a minus b equals to 0 dash. So by using homomorphism condition, psi of a minus psi of b equals to 0 dash. So therefore psi of pi of a is equals to pi of b. So we are taking u of a, u plus a is equals to u plus b. We are getting pi of a is equals to pi of b. So therefore the mapping psi is well defined function. So well defined function is nothing but u plus a is equals to u plus b. We have to show that psi of pi of a is equals to pi of b. So this is well defined condition. So next 1-1. So 1-1 condition. How to verify 1-1 condition? So f of x is equals to f of y condition. f of x is equals to f of y, we have to show that x is equals to y. So this is one condition. So f of x is equals to f of y, that implies x is equals to y. Indirectly is nothing but so reverse steps of well-defined function. So well-defined function is nothing but x is equals to y. We have to show that phi of f of x is equals to f of y. So but here in one condition, so f of x is equals to f of y, we have to show that x is equals to y. For any a comma b belongs to R, psi of u plus a is equals to psi of u plus b. So now we have to show that u plus a is equals to u plus b. So psi of u plus a can be written as phi of a. So psi of u plus a is equals to phi of a, and psi of u plus b is equals to phi of b. So u plus a, pi of a minus pi of b is equals to 0 or 0 dash. So pi is homomorphism. So then we can write pi of a minus b is equals to 0 dash. So this can be written as a minus b belongs to u, because this is defined as kernel u. So that's why size pi is homomorphism with kernel u. So psi of pi of a minus b is equals to 0 dash, then a minus b belongs to kernel pi or kernel u. So a minus b is equals to belongs to u. So a belongs to u plus a belongs to u plus a, and next step u plus a is equals to u plus b. So this is one condition. Psi of u plus a is equals to psi of u plus b. That implies pi of a plus pi of u plus a is equals to u plus b. So this is one condition. So well-defined condition and so first we have to verify well-defined and so next one condition. So next so clearly size onto. So onto condition is nothing but every element in codomain, there is a pre-imaging domain. So here, so pi of r. So pi of r is a codomain. So every element in codomain, there is a pre-imaging domain r by q. So that's why clearly size onto condition, size onto. So it satisfies well-defined and onto one condition and onto condition. So last one, size homomorphism. Psi of u plus a plus u plus b is equals to psi of u plus a plus b. So sum of two ideals u plus a plus u plus b can be written as u plus of a plus b. So psi can be defined as psi of u plus a is equals to phi of a. So here also psi of u plus of a plus b can be written as phi of a plus b. So phi of a plus b can be written as, so pi is homomorphism, pi of a plus pi of b. So but pi of a is equals to psi of u plus a, and pi of b is equals to psi of u plus b. So therefore psi of u plus a plus u plus b is equals to psi of u plus a plus psi of u plus b. So this is first condition of homomorphism. So next second condition, psi of u plus a into u plus b. Psi of u plus a into u plus b is equals to psi of u plus a into b, the product of two ideals u plus b. So pi of a into b. So by using this condition, psi of u plus a is equals to pi of a. So psi of u plus a into b is equals to pi of a into b. So pi is homomorphism. So we can write pi of a into pi of b. So but pi of a is equals to psi of u plus a and into psi of u plus b. So this is second condition of homomorphism. So psi is well-defined function, size 1 and on to first condition of homomorphism, the second condition of homomorphism. So therefore size isomorphic to pi of r to r by u. Okay, so this is the theorem. So if pi is an epimorphism, then pi of r is equals to r dash. In particular case, in particular pi is epimorphism, then r dash is isomorphic to r by u. So here we are taking pi of r is equals to r dash. Hence, r by u is isomorphic to r dash. So this is next case. So this is very important theorem, fundamental theorem of homomorphisms of a ring. So question, state and prove. State and prove fundamental theorem of homomorphisms of a ring. The next statement, for any positive integer n, z by n into z is isomorphic to zn. So these are the only statements. This is known in Chinese Remainder theorem. Statement. If m and n are relatively prime positive integers, then zm into n is isomorphic to zn cross zm. So these are the statement. Z n into m is isomorphic to zn cross zm. Next, integral domains. So in this total 8th chapter, so ideals and homomorphisms. So this is very important theorem. So next, ideals and integral domains and fields. Next, 9th chapter. What's the definition? A non-trivial commutative ring R with identity is called integral domain if it has non-zero divisors, that is a into b is equals to 0, a belongs to R, comma b belongs to R. That implies that a is equal 0 or b is equal 0. A non-trivial commutative ring with identity is called integral domain. So integral domain definition. So R comma plus comma dot is a ring. So R comma dot is commutative. So first condition, R comma dot is commutative. So next R comma dot is satisfies identity condition. So R comma dot is satisfies identity condition, and also it has no zero divisors. So zero divisors is nothing but a into b is equals to 0. Either a is equal 0 or b is equals to 0. B is equal 0. So 0 divisors is nothing but the product of two numbers is equals to 0. Either at least one of the element should be equals to 0. Either a is equal 0 or b is equal 0. It has no zero divisors. A commutative ring with unity is said to be integral domain if it has no zero divisors. So it satisfies commutative condition. Identity is nothing but like identity condition, and also it satisfies no zero divisors condition. A into b is equal 0. Either a is equal 0 or b is equals to 0. So this is integral domain definition. So next, the characteristics of integral domain is either 0 or prime number. The characteristics of integral domain should be 0 or prime number. These are the proof is known. So next definition, division ring and field definition. A non-trivial ring with identity is said to be a division ring or skew field if it has no non-zero elements from a group under multiplication. Every non-zero element has multiplicative inverse. So like so field definition. So first ring definition ఏంటంటే R, plus is abelian group. Ring definition R, dot is semi group and left distributive law and right distributive law. So here R, plus is abelian group. So ring is nothing but here two binary operations. So first one is addition R, plus, dot. So second binary operation is multiplication. So ring is nothing but R, plus is abelian group. So abelian group is nothing but all conditions are fulfilled. 5 conditions. So next R, dot is semi group. Here only 2 conditions. So here 3 conditions are left. First one identity, inverse, and commutative. So here 3 conditions are. Here only 2 conditions are satisfied. Semi group is nothing but closure and associative. So next left distributive law and right distributive law. So ikkada 3 conditions remaining. So remaining 3 conditions base చేసుకొని so integral domain and field definition and uh, Q field definition. So these are based on R, dot. R, dot should be commutative. R, dot should be identity. R, dot should be uh, inverse condition, and also no zero divisor sign. It has zero divisors. So like this. So here field definition. So field definition is nothing but a commutative division ring is called field. A commutative division ring. So division ring is nothing but R, dot. So previous ring low R, dot. So R, dot is group. So group is nothing but it satisfies closure, associative, identity, inverse. So it satisfies with respect to multiplication, it satisfies 4 conditions. So then we can say that is a division ring. So field is nothing but R, dot is abelian group. It satisfies all the conditions. R, plus is abelian group. R, dot is uh, abelian group and left distributor law and right distributor law. So a commutative is nothing but it satisfies commutative condition like abelian condition. A commutative division ring is called a field. That is, a field is a non-trivial commutative ring with identity in every non-zero element has multiplicative inverse. Is nothing but it satisfies inverse condition and identity. So here identity, inverse, and commutative. So 3 conditions. So R, dot is semi-group, and so remaining 3 conditions identity, multiplicative inverse, and commutative division ring. So it's nothing but commutative condition. So like R, dot is abelian group. Okay. So this is the definition, field definition. So next, any field is integral domain. So any field is integral domain is nothing but so integral domain, and also here any finite integral domain is field. Any finite integral domain is field and any field is integral domain. So this is proof. Let R be a field. R is non-trivial commutative ring with identity and every non-zero element has multiplicative inverse to prove that R is integral domain. So now we have to show that capital R has no zero divisor. So there is a difference between integral domain and field. So integral domain has non-zero divisors. Integral domain has non-zero divisors is nothing but it has no zero divisors. So we have to show that R has no zero divisor. Let A comma B belongs to R, A naught is equal to 0 and A into B is equals to 0. Since A naught is equal to 0, R is a field, then there exists a inverse. Then there exists a inverse. A inverse belongs to R such that A into A inverse is equals to A inverse into A is equals to 1. So here we are taking A inverse on both sides to A into B is equal to 0. A inverse into A. So taking inverse on both sides, A inverse into A into B is equal to 0. A into A inverse is equals to 1 or I. So we are getting B is equal to 0. So A into B is equal to 0. A naught is equal to 0. That implies B is equal to 0 in R. So thus R is integral domain. The converse of this theorem is need not be true for Z is integral domain, which is not a field. However, if any integral domain is finite, then must be field like this. Any finite integral domain is always field. So here, so similarly, we are taking B inverse on both sides. We are getting A is equal to 0. A into B equals 0. B naught is equal to 0. We are getting A is equal to 0. So these are the R has no zero divisors condition. So therefore, any field is an integral domain and any finite integral domain is field. So next, maximal ideals and prime ideals. So very important topic. Maximal ideal definition. An ideal M naught is equals to R in a ring capital R is said to be a maximal ideal of R if whenever U is an ideal of R such that M subset R is equals to U subset R is equals to R, then either M is equals to U or U is equals to R. So maximal ideal definition. So M is not is equals to R. M is not is equals to R, and so U is ideal of U is any ideal of R. U is any ideal of R such that M is subset R is equals to U, subset R is equals to R. So first condition, M is not is equals to R. M is ideal line, R also ideal, and U is any ideal of R. U is any ideal of R such that M is subset R is equals to U is subset R is equals to R. M is subset R is equals to U subset R is equals to R. So between these two ideals, M and R, there exists a U ideal. Then there exists a U ideal such that either M is equals to U, M is equals to U, or U is equals to R. It's clear? So there is no ideal between M and R. So this shows that there is no ideal between M and R. In case any ideal exists, it should be is equals to M, or it should be is equals to R. Either M is equals to U or U is equals to R. Is clear? It is nothing but there is no ideal between M and R. In case there is an ideal exist between M and R, it should be is equals to M, it should be is equals to M, or it should be is equals to R. So this is the ideal definition, maximal ideal. An ideal M naught is equals to R. In a ring, R is said to be a maximal ideal. So whenever U is an ideal of R such that M subset R is equals to U subset R is equals to R, then either M is equals to U or U is equals to R. Is clear? If there exists any ideal between M and R, that should be is equals to M or equals to R. So next one. So this is important theorem. So let M be a proper ideal of commutative ring R with unity, then M is maximal ideal if and only the quotient ring or factor ring R by M is a field. So before theorem, so prime ideal definition. So this is prime ideal definition. Let P be an ideal of a commutative ring with unity. P is said to be a prime ideal if P not is equals to R, or any A into B belongs to R. So either A belongs to P or P belongs to P. So prime ideal definition. So P is said to be a prime ideal if A into B belongs to P, either A belongs to P or B belongs to P. Then we can say that P is a prime ideal. So let P be an ideal of a commutative ring R with unity. So P is said to be a prime ideal of R if P not is equals to R, or comma B belongs to R. A into B belongs to P. That implies A belongs to P or B belongs to P. So this is prime ideal definition. So maximal ideal definition and prime ideal definitions. So these two. So next theorem. So important theorem. Let M be a proper ideal of a commutative ring R with unity. Then M is a maximal ideal if and only the quotient ring R by M is field. R by M is a field. So prove, let M is a maximal ideal of R. So M is a maximal ideal of R. Consider factor ring R by M. So evidently R by M is a commutative ring with unity. Because so R is a commutative ring with unity, then R by M also commutative ring with unity. So we have to prove that there is only ideal of R by M or R by M, and then R by M is a field. So M and R by M is a field. So here we have to show that R by M is a field. Okay? If M is a maximal ideal, then we have to show that R by M is a field. So we know that there is a canonical homomorphism pi from R into R by M with kernel M. Also, there is a 1 comma minus 1 correspondence between the ideals of R by M and the ideals of R which contains M. So clearly, so this is total theoretical part. So we know that there is a canonical homomorphism pi from R onto R by M with kernel M. So canonical homomorphism from R to R by M with kernel M, and also it is 1-1 condition. So 1-1 correspondence between the ideals of R by M and the ideals of R, so which contains M. Under the correspondency, the zero ideal M of R by M corresponding to the ideal of R by ideal M of R, and the ideal R of R corresponding to the ideal R by M of R by M. So this is total theoretical part. So therefore, there is an ideal U bar such that M subset R is subset to U bar subset to R by M. So first, so a canonical homomorphism pi from R to R by M. So we are taking a homomorphism pi to pi from R to R by M. So it satisfies homomorphism conditions. So with kernel M. So with kernel M, so this is, so we are our assumption pi is a homomorphism from R to R by M with kernel M. And also there is a 1-1 correspondence between R by M and the ideals of R. So there is a 1-1 correspondence between is nothing but it satisfies almost 1-1 condition. So our defined mapping is satisfies 1-1 condition. So there is a correspondence between 1-1 condition between R by M to R. There is a corresponding 1-1 condition between R by M and the ideals of R. So which contains M. So which contains M is nothing but which contains kernel. So here M is nothing but M is defined as kernel. So under the correspondency of zero ideal. So M is nothing but this is zero ideal. So 0 plus M. So 0 plus M of R by M corresponding to ideal M of R and the ideal R to R corresponding to R by M of R by M. So therefore, so U bar is nothing but U bar is a another ideal between M and R by M. So by using maximal ideal definition, so there is an ideal between M and R by M. That ideal should be must be is equals to M, or that should be is equals to R by M. So we must have U is equals to X belongs to R such that pi of X is equals to U bar such that M subset to U subset to R. This is a contradiction to maximality of M. So which is contradiction to our assumption. So because so this is not possible. So it is only possible when M is subset to U subset to R. So this is contradiction to maximality. So therefore, hence, so there is a not any ideal between R by M and M. So by using maximality condition, there is no ideal between M and R by M. So therefore, only ideals of R by M and R by M and M, hence R by M is a field. So clearly here there is no ideal between M and R by M. So therefore, so R by M is a field. So conversely assume that M is maximal ideal of R such that R by M is a field. So now we have to prove that M is maximal ideal of R. Since R by M is a field, it is only ideal R by M and M. If M is not a maximal ideal, then there exists a ideal U of R such that M subset U subset to R, but we must have U bar equals to pi of X such that X belongs to U such that M subset U bar subset R by M. So this is contradiction to fact R by M is a field. Hence M is maximal ideal of R. So ikkada we are taking M is not a maximal ideal. So but we have to show that it is a maximal ideal. So but we are taking contradiction. M is not a maximal ideal. Then there exists a ideal U of R. So we are taking another ideal U of R such that M subset to U subset to R. So but we must have ideal U bar is equals to pi of X such that X belongs to U such that M subset to U bar subset to R by M. So which is contradiction to our assumption because M is subset to U subset to R. So this is contradiction to fact R by M is a field, hence M must be maximal ideal in R. So this is R by M field condition. Next theorem. Let P be a proper ideal of a commuted ring R with unity, then P is prime ideal of R if and only if R by P is integral domain. So proof, we know that for any A belongs to P, comma P plus A is the zero element of R by P. So R by P is nothing but factor group or a factor ring. R by P if and only A belongs to P. Thus, for any A comma B belongs to R, so either A into B belongs to P. That implies A plus A into B is equals to P, the zero element of R by P. So if and only if P plus A into P plus B equals to P, and A belongs to P or B belongs to P, so that implies P plus A are P plus P is the zero elements of R by P. So thus P is prime ideal of R if and only if R by P is integral domain. So here we are using prime ideal definition. So P is prime ideal if and only if R by P is integral domain. So prime ideal definition is nothing but A into B belongs to P, either A belongs to P or P belongs to P. So we know that every A belongs to R. Every A belongs to R. So in R by P, each and every element in R by P is of the form P plus A. P plus A is the zero element of R by P. So P plus A is the zero element of R by P if and only if A belongs to P and A comma B belongs to R. A belongs to P comma A and B, A comma B belongs to R. So A into B belongs to P because we are using prime ideal condition. So prime ideal if and only if R by M is R by P is integral domain. So A into B belongs to P. So if and only if, so zeroth element in R by P. So zeroth element in R by P is P plus A into B is equals to P is the zeroth element of R by P. So P plus A into B is equals to P. So this can be written as P plus A into B can be written as P plus A into P plus B equals to P. And so here A into P, A into B belongs to P. Either A belongs to P or B belongs to P. So if and only A plus P plus A or P plus P is the zeroth element of R by P. So thus P is prime ideal of R if and only R by P is integral domain. So these are the ninth chapter. So in this ninth chapter, so this is very, very important question. 6.9.6.2 theorem. R by M is field question. And this is also fundamental theorem of homomorphisms of a ring. State and prove fundamental theorem of homomorphisms of a ring. So we'll see in next class.
అయిపోయిందండి క్లాస్ సుంట
నెక్స్ట్ క్లాస్ లో చెప్తాను.
అయిపోయింది.
Thank you, sir.
సార్ అసైన్మెంట్ ఎలా రాయాలి సార్?
అసైన్మెంట్ మీకు ఎక్కడమ్మా మీది అక్కడ అడగండి ఒకసారి చెప్తారు.
మాది వరంగల్ అడ్మిషన్ సార్.
అక్కడే అడగండి చెప్తారు ఎలా రాయాలో.
అవును, ఓకే సార్. సార్ అసైన్మెంట్ కి లాస్ట్ డేట్ ఎప్పుడు సార్?
సైట్ లో ఉంటుందమ్మా. ఈ మంత్ 30 అనుకుంటా, చూడండి ఒకసారి. 31st.
ఓకే సార్, థ్యాంక్ యూ సార్.